We're trying a new process in this meeting, as you know. We've discussed it a little bit before, in that we've asked you to post questions that you have for speakers on the wiki, and a few of you have done that. I hope more of you will do so in the next two talks. But this is the first time that the students and postdocs have a chance to address those questions. So this very brave team of young researchers has volunteered to try to answer the questions that were posted in the past couple of days. And I'm not quite sure how they've organized things. We haven't tried to manage this at all. And so I turn the floor over to the head wiki leader, who is...
Nobody. We're headless.
You're an elastic.
Yeah. Well, if you have something, you should.
Yeah, and then I'll just
So one thing is, we have looked at the questions earlier today, and there was, I think, 6 or 8 of them. We discussed them a little bit, and we discussed who was going to present which and have some ideas. And then we all went to the beach and went swimming, and then came back, and consequently there were, of course, 20. Not quite, but there are more. So some of them may be a little bit on the spot, so we may ask the relevant experts in the audience. Let's see how that goes.
Okay, I'm going to try to first go on one of the questions, which is, why might one expect pressure and doping to do the same thing to superconductivity if in some systems the lattice contracts behave completely the opposite for doping versus pressure? What other parameters could doping and pressure be tuning? Okay, so first of all, we had the example on the barium 122 barium iron arsenide. We apply pressure, and we see superconductivity appears. So to sort of answer that question, I wanted to come up with another example that actually to me is a bit more familiar, which is the 111 compound, lithium iron arsenide, which seems to behave the same way. So there was a paper out on PRB a while ago saying if we apply pressure to lithium iron arsenide, we can see that the lattice constants change, and they actually change in the same way as they would go from the arsenide to the phosphide. And as they basically do that, they see the same, they reach a point where you apply enough pressure, so you come to the same point where the phosphide would actually be. So if you measure the phosphide in transport, you basically see the same critical temperature. And if you do X-ray on that, what they have also done under pressure, you can see that the lattice constant changes in a way that it should be while you're doping, which does suggest that basically doing an isovalent replacement of arsenide with phosphide actually gives you a sort of chemical pressure, chemical potential in your system, which causes your lattice to basically shrink or expand, and that can be different for different dopings. That's why there are different effects coming in. But overall, you can, starting on the arsenide side and applying pressure, you can get a similar picture as doping it, which is basically due to the lattice characteristics. And if we take that then a step further, and we would think about okay, we change the lattice constants, and we do band structure calculation on that. What we get is basically a change in the density of states at the Fermi level due to the change in the parameters. And so basically, the density of states is linked to a couple of things that we can measure: heat capacity, resistivity. So usually we refer to resistivity because that's the easiest to measure under pressure, because it's very hard, if not even impossible, I don't know of any paper measuring heat capacity under high pressure. But there are certainly other possibilities to measure that. Other possibilities to see that. Did that sort of answer the question?
Can we follow up with further questions and discussions?
Yeah. Okay.
No, I mean, I want to ask if you know, since you know something about this.
Okay. Yeah.
We have several examples where we have phosphorus arsenic analogs.
Yeah.
And do we know if the lattice constants are always changing in the same way, and if other system properties also follow this? I mean, there's the 1 to 2 system and...
Yeah, so there's the 1 to 2 system, which was also shown before yesterday, seeing that there's a linear dependence in the c-axis parameter, or in the c-axis value. That was shown by the group of Kasahara, and we have been using that in our measurements as well on the 1 to 2s doing the HVA, and basically comparing, let's say, TC to what that z-axis value is, and it fits quite well to this linear behavior in the change. I'm not quite sure of any other examples except of that one and the variant 1 to 2 where the change happens. Or if it's like always in the same direction, if the c-axis value always shrinks linearly, or if there might be a more complicated
Do we know about LaFepo and the one on one? Okay, yeah, we know either.
Yeah.
Okay.
Just a tiny comment on the 1111. If I remember correctly, there the difference between the arsenic and the phosphor is more in the height of the nitrogen atom over the plane than the constant. So it may be a little bit delicate to transfer from one system to the other.
In E?
So
And
the
then-
different parameter, which is the arsenic or phosphor height over the iron arsenic plane.
Yes.
And that changes actually the topology of the plane. So
Yeah, but that also changes in other materials. So there was a paper out on the Kasahara group just last week saying if you look at this nitrogen height, so basically the iron arsenide distance, this varies a lot for different materials, and so they claim this is actually something that might give you a hint for nodes on the thermal surface. So it's not just in the doping, but it also varies between different compounds.
I'm here to add something on my previous artist data about the iron chalcogenide samples. So the thing is, I have made a series of iron chalcogenide samples as a low iron telluride as a parent compound and low dope selenium dope level. And as we add selenium into iron selenium, we have the c-axis shrink, and then the three-dimensional characteristic in the electronic structure of this compound become more and more, it's getting stronger. And we have similar experience on LCO. So we did something like we made thin films on STO substrate, and when it's really thin, the thin film, you have lattice strains, so you have pulled the lattice parameter like that, and the electronic structure became 3D, like a cheese, like that. So it seems like when you change the lattice parameter, when the c-axis is shrinking, and it's like you are enhancing the hoping in Z direction, and then the three-dimensional characteristic is enhanced by this kind of lattice changing.
Can we know which button raises the screen?
Raises the screen.
I can start counting and then we might
Yeah,
switch to the dark.
random combination
Yeah.
of keys and see. The lower line.
The lower line. Also not. Okay. I think you have to use the small one.
That's too small for you?
I'm asking him.
Oh, should be okay with you, it's fine.
Oh,
Oh, yeah, we ordered that, and we just have all the others.
Oh, yeah, okay, it's fine.
Okay, so yeah, I'm sort of a bit focusing on the experimental side, so I'm not that great expert on theory. Okay, next question I selected here was, is it possible that by applying external pressure, you're also introducing disorder? Example, applying non-uniform pressure across the crystal or by some intrinsic effects. Is there a way you can actually verify that this is or is not happening? Okay, so what I'm showing here is an example of one of those pressure cells. So taking that from a paper from the Tozer group from Tallahassee. So what you see here is basically a diamond cell. They're determining basically the pressure by line shift in a crystal before placing the cell or close to the cell. And basically what you see here, this kind of spot, is the sample, and they surround it by a silicon liquid, which basically means they have a hydrostatic pressure. So it's not like you just have a uniaxial strain that you just prep on like one side of the sample where it is actually possible if you're not perfectly aligned and the surfaces are not perfectly parallel. That you actually introduce some defects in the sample. But they actually have like a uniform pressure on the sample which reduces this effect. And well, is there a way you can actually verify that this is not happening? Well, the best way that they verified so far was in the barium iron arsenide. There was a great challenge to actually see quantum oscillations because of twinning. And what the group from Hiroshima did just recently, there's published on the archive, is they applied pressure along the z-axis, actually along the b-axis, sorry. And you can see that there is a change in the resistivity. And due to that, they were able to see quantum oscillations, which is not possible if you would basically introduce defects into your sample significantly by pressure. So, well, people doing that take great care of that this is actually not happening, that you do not introduce disorder, but it needs basically very special experimental setups to actually do that. And it's not straightforward to do so. Yes, it can happen, but it's basically controllable, I would say. Any further questions?
Is that the last one?
No. Sorry, there's more. There were a lot of questions. A little bit about pressure. About the pressure dependence of TC and 122 family substitution of arsenide and phosphide does not change the density, charge density. Is this a system where doping should behave exactly as pressure? Has it been measured? Yes, it has been measured. This is a reference. Well, sort of quick answer. And what they see is, as they apply pressure, superconductivity hits in. If they keep raising the pressure, superconductivity fades back out. So above 7.5 gigapascal, they claim that there's only small, maybe at 8, there's still signs of conductivity, but afterwards it vanishes. Which sort of behaves like the superconducting dope in barium iron arsenide phosphide. When you dope it, first superconductivity hits in, and then it fades back out. And this also, at around the optimal doping, they see that this spin density wave transition in the resistivity goes away. So this sort of also follows the behavior by doping. So obviously, yes, it's possible, and yes, it has to be measured.
So the pressure measurement was done in the phosphorus or in the barium iron arsenide?
This is in the barium iron arsenide.
Okay, so it puts pressure that is similar to phosphorus.
So if you apply pressure, it's getting to the phosphorus side, like also in the 111 lithium ion arsenide. If you apply pressure to the arsenide, you shrink the lattice, and then you end up on the phosphorus side. That seems to be consistent in different types of materials.
So does that correlate with what you said about the nutrition height?
Well, the pnictogen height is also affected. I mean, if you compress your c-axis, what we've seen yesterday is you can, or this morning actually, is like you can have the arsenides bound at some point, right?
Yeah.
But also, I mean, there is a repulsive force there, which is basically not just compressing the c-axis, but it's also compressing this triangle iron arsenide, right? And it's compressing that. Which is one of the reasons. So where this has been done is, again, lithium ion arsenide, lithium ion phosphide, where you can see that the pnictogen height varies between the arsenide and phosphorus side. And well, again, back to the picture from Sahara that I mentioned earlier before, one has nodes and another doesn't. More question?
Just a comment. I think the equivalent thing happens in heavy fermion, uranium, ruthenium 2, silicon 2 in the phase one. Just a
I'm an
comment.
expert in that, so sorry. Any other questions on that?
Shall we do coexistence?
Yeah.
There was one last thing that I didn't complete answer. I didn't have time to look like a reference or something. You told us, okay, is the Papillon, is the pronouncer hopefully correct. You told us that pigfights have higher HC2 than group rates, and that's good for application. I was wondering about the reason of this. In fact, group rates are higher TC, and I thought TC and HC2 may be linked with the strong superconductivity. Well, I mean, there's more than to it than just TC. I mean, it depends on the limiting effect. You have order limiting effects, you have like spin limiting effects. Right? There can be different things, and they can determine they basically determine HC2. And I know I know materials where HC2 also has been overestimated by just measuring up to 10 Tesla, saying, okay, we apply some model, and they came up with 50 Tesla for the 111s, and it ended up being 18 Tesla. So, I mean, there can be overestimates. I'm not really sure. I didn't get that point in the talk, that it's actually higher than the group rates.
No, I don't think it's true.
So,
It's not.
I mean, I recall like IPCO having something like 300 Tesla or something.
Well, that's an estimate.
Yeah. Okay, let's say it's higher than the highest pulse field we have at the moment.
I remember one remark about applications, which was that pinning was probably better.
So,
in
yeah, so
and that's
Yeah.
good for applications.
yeah, so the pinning effect can be quite different. So you usually you can have low pinning effects in the big fights. And also due to the metallic behavior, it's much easier to make wire for most of them. That's the main point. Where on like IPCO, it has a high control field, but there's a ramming to it. You have to make tapes.
I guess for most applications where it's 18 or 300 Tesla, that's fine.
I remember one important factor is the high carrier density.
Well, actually, the main problem is grain boundaries for the practical guys. They only care about grain boundaries. That is why magnesium diboride is very good for us. Very boring for theorists, but very good for making wires because the grain boundaries are not so killing. And as far as I know, grain boundaries is a big problem in the lake labs.
Because of sample growth, or
For making wires, so if grain boundaries are destructive, you have to make a wire that's a single crystal, and that's kind of problematic. Well, because
Is there already some studies on aggregate?
Yes. Yeah, it's very similar to YBCO. Very strange, but very similar. Only 2 or 3 angles, but okay, preliminary results.
Okay.
thank you, Carsten. And then switch to questions. There's some questions that are more here. So there was a question about the coexistence of magnetism and superconductivity, and as it turns out, we have an expert who's standing over there. Go ahead. So we're going to turn that one over.
Just need to tell me which one you need.
It's the one that's already answered.
Oh, there.
So aside from the answer that's already there, we're going to give you a different perspective.
Yeah,
Is
so
that a different answer?
this perspective is essentially in the adjuvant thing. So to get started, we've been working in this field, you already know this, but just for the general audience, the typical Williamson structure that we have for the ideal superconductors, at least in the toy case for discussion, it will be good, is that we have a whole pocket at the gamma point in the center, and this comes from one band, and there's another electronic band which cuts the Fermi surface at 2 locations. One is here and one is here, giving 2 electronic pockets. Now, the question about existence of the magnetic order, that can be looked at in the following way. We can consider two vectors here, Q1 and Q2. We can call them as nesting vectors. For whatever reason, we can discuss that later. One of these vectors is selected for the development of the magnetic order. So, for example, suppose Q1 is selected. That means an antiferromagnetic order will be developed by the mixing of this whole pocket and this electron pocket. And that leads to a reduced Brillouin zone where these two mix. This is folded back onto this one, and you get something like this. This electron pocket survives. It does not participate in the formation of the magnetic order. And in this case, it's essentially the mixing of this whole band and the electron band here. Since their dispersions are electron and hole like, what happens is an SDW gap is by GW on spin density rate. Gap opens up wherever they intersect, and depending on the magnitude of the gap, that is the strength of the order parameter that is developed, a large gap opens up. What is interesting is there are still residual Fermi surfaces which are left. One can call them as the reconstructed Fermi surface in this new Brillouin zone. Now, when we talk, the question that is put forward there is, well, if this has already taken part in the formation of the magnetic order, can this band give rise to superconductivity? Which naively one will say yes, which is fine. This by itself can lead to superconductivity with K minus K kind of a pairing. Well, it's K minus K because you can pull that back there and it goes. But there's a much more interesting thing, that is, this pocket can entirely be forgotten. In the sense, you can have superconductivity even in this reconstructed Brillouin zone. From the residual, whatever interaction existed between these pockets, from the residual pockets which are here, interaction still exists between these points which are K minus K related. I'm sorry, it will be here. And superconductivity is possible even just within this. So, and this is, in my opinion, slightly more interesting form of coexistence, so to speak, because it's the same electrons which form the magnetic order are actually giving you superconductivity. It's just the residual fermions which are there. You don't even need the free band which is outside, which do not actually do anything to the magnetic order. So, and this has been looked into before, and we are also looking into this to address issue of loads and etc. After the summer school, something will be related to that. So, that's essentially it. Like, yes, the answer is true, but then you have sort of two different kinds of coexistence you can think of. One is the naive one where this will be superconducting and there's nothing here. The other one is much more interesting, where the same fermions give rise to the magnetic order and superconducting order. Just a word of caution, for this to happen, we need to have the electronic pocket to be elliptical. That is the only reason these pockets survive. If they were completely circle and of the same size, they would nest exactly, gap out the entire Fermi surface, and you don't have anything else. And in that case, the coexistence will only come from here. So that's essentially what I had. If you have more questions, or if it's not here, I can go again.
What's the lead situation?
Sorry?
What's the lead situation?
Most likely this. To start with, they are elliptical for sure. And depending on doping, well, you can really shrink them, depending on materials. If they shrink completely, then you have to get to incommensurate momenta to see these. I don't want to comment on that. Yeah.
But then can you explain that we see how to see the orbs when you go?
Not.
When you go deep into the magnet.
I don't think from this analysis it's that easy. Because theoretically, when you just solve linearized gap equation, which tells you the gap structure, but to get to TC, you have to.
Oh, but you have lost Fermi surface, right?
Sorry?
You have lost Fermi surface.
Yes.
So I think it's fairly natural that you see
Oh,
what
well,
goes
yeah,
out.
okay. In that sense,
Yeah.
yes, yeah. Yeah, compared to the case where you have.
Compared to the
yes,
previous
that
case,
it will go
yeah.
down for sure, yes.
Okay.
And that's.
Shall we do symmetry?
Good? Good. Okay, there were two questions that were related to E-G and T2Gs.
We are more below now.
No, one was just up there, which is this one, with x squared minus y squared and xy orbitals look the same, just a little bit rotated. Why are they different enough to be in different E-G and T-G suborbitals? And now, and there was, just to already mention the second question, if you go to the very bottom, there's some external parameter that can deform orbitals, such as lattice deformations, and I feel they're somewhat connected, and I'm not sure how everyone understands what this T2G EG is all about, and so I thought I'd first give a little bit an intuitive picture why x squared minus y squared and xy are not like the same, and a little bit why just pure lattice deformations don't really matter that much for the shape, or don't change the shape of the orbitals. And then I tried to give a little bit a reason why you have all these funny abbreviations, T2G, EG, A2G, B2G, without, I hope I don't, it doesn't get too bad.
No character.
No, I tried. Okay. Anyway, so the simple reason why we even start with the whole, I mean, it is all connected to symmetry and what the symmetry of your lattice is. And the question is basically, I have my atom, or my ion in the middle here, and I have an orbital that I put there. And the question is, are all these orbitals, for example, in the D shell I have 5, are they all exactly the same? Or does the lattice do anything to them? And so, if I have a relatively simple picture, or a simple thing, as I have in the, for example, perovskites, or just in all these systems where, here I try to draw an octahedra around the ion or atom that I want to look at. If the system is as simple as that, then I can just draw orbitals and basically guess, or just see by looking at them, which are the same and which are not, which is one of the things we have seen in this morning. So for example, if I take that xy, that looks more or less like this. So it points along, these nodes point, or this node points along the diagonals. And so if you think of this as here having atoms and here having an atom, or here having charges, and this is an electron that is a charge, then this situation is definitely different from this situation, where, oh no, this one goes in this direction. I don't know, maybe from the situation where these point exactly towards the ligands, so for example oxygens. And so even though there's just rotation between them, these are inequivalent, and that's why they're in different, or they're differently grouped. However, if you look again at the this xy that I've drawn first, since this thing I can rotate around any axis, and it's a symmetry, so it stays the same. I can make out of the xy, I can make an xz, I can make a yz, and therefore these orbitals xy, yz, and cx, they're equivalent, because from an energy point of view, they shouldn't care, and they belong to T2G. And the other two that I have, so the x squared minus y squared and the 3c squared minus r squared, they belong to EG.
Over square root of 3, right?
Exactly. And that these are the same is not so simple from just looking at a picture, but you can for now, just delete that. And now I can look at lattice deformations. And a very simple lattice deformation that I can make is I take these two and move them closer here. And what you can already tell, if you look, for example, at these again, the x, y versus the yz and the zx, they're different because two of them are pointing in this direction. So one like this, one like this, and the third one is in the plane. So they will definitely, the energy of them will definitely change in a different way. And so what will happen? I write that just like this. So I have this one is 3 times degenerate, and what will happen is I get a B2G and an EG. And you can do the same with these. They will, of course, they will split up to, I don't remember in which of these little letters. And so that's, for simple systems like this, we can just look at it and move around ions, and that works quite well because we can just, yeah, it's pretty obvious. Now if you have slightly, okay? Sorry.
So in this case, the higher energy states are YZ and XZ?
I would guess so, yes. Because if you look at where the electron sits in the XY, it's in the plane. And so when you move the negative charge closer, it doesn't matter that much, but the others point out of the plane. And so they should feel that more. And so if you have simple things, it's pretty simple to look at it, but if you have slightly more difficult environments, I mean, even in the iron pnictides, I don't like to think of the arsenic that sit around. Then it's much easier to do the whole exercise, not by looking at orbitals and how they look in this picture, but to do the whole thing with symmetry analysis. And then you end up doing group theory a little bit, but not. It's not even that bad because all you have to look at, if you don't care too much about the math of group theory, then the only thing you have to care about is to know that there's irreducible representations for a group, and that they transform differently under the symmetries that this symmetry group has. And so if you, I mean, the simplest symmetry that you can have is, for example, identity, so you don't do anything to your crystal, or if you have this octahedral thing again, I'm not going to tell you all the symmetries, but for example, you can imagine you have an axis here that you can rotate by 90 degrees, and you get the same structure. And you can do that in many different ways. So you have all these different symmetries, and all you have to know is which irreducible representation transforms how under which symmetry. And then you can look at how high is the degeneracy, and how do the orbitals fall into this irreducible representations. And so if we take, for example, this octahedral, then what we see is that there's an irreducible representation, now capital letter T2G, which is 3 times degenerate, and there's basis functions that are given by x, xy, xc, and yz. And so you see already, these are exactly the basis functions that we have for the orbitals. So these corresponds to these basis functions. And you can look at others. So there's whole character tables that you can look at what irreducible representation has any symmetry that you like. And there's EG, and then there you exactly have x squared minus y squared, and 3c squared minus r squared. And now, I mean, till you get to that, that's a little bit, you have to learn a little bit about group theory, but now the nice thing is, you can ask, what happens now if I deform my crystal? Because if I deform my crystal and go with these down to here, then you see immediately some of your symmetries are lost. And you can just go and look which of the symmetries are lost and what is the new symmetry group that that corresponds to. And if you do that, then you end up with D4H. This is again just not names for all these different symmetry groups, but you can then look at actually you can use character tables then, and what you see is that if I go from OH to D4H, they tell you that T2G will become EG plus B2G, and here I don't remember. So you can just look at these character tables, get these out, and that basically, if you then talk of orbitals, you just say T2G, and here you call them EG and B2G. And so all these names of EG, T2G, A1G, and so on, it's just coming from group theory, coming from classifications of irreducible representations, which, if you want to exactly know how you split orbitals, then they're very useful, but apart from that, they're just names. And the only thing, I tried a little bit to figure out what all these names mean. And I didn't get the real answer. I don't know whether anyone really knows in here what the answer is, but what you find, you find A, B, E, and T. That's the usual ones that you find. And then 1, 2, 3, and often, if you have orbitals, it's always G, but you can also have AU. G is the good old thing that it always means it's German gerade, ungerade, even and odd, which means if you make inversion that it's odd or it's even or odd under inversion. And then what is nice to know, because if someone just tells you it's EG or it's B2G, is these two are always one-dimensional, this is two-dimensional, and the T is three-dimensional. I tried to figure out whether it has anything to do with German abbreviations, but I don't think so. But so, as soon as you see somewhere orbitals T2G, it's always 3 times the generate. And the last thing that I am not completely sure, but I think it's true, AG always transforms trivially under the highest rotation axis, which means if I have a 4-fold rotation, AG will not change anything, and B will always change the sign. And so that's all I could figure out about that. And I say that because we were discussing about that yesterday at dinner. So much for symmetry. Any questions?
I have a related question. Actually, I wondered, never knew why. Is there a reason for this notation 10dq?
And to Tom's defense, he said, I have no clue why.
It's 6 plus 4.
More? Alright, I'll take over from here and also do a little bit of symmetry. This one we tried to guess at, so we have sort of a guess. This is for the Syrian atom. Right, and the point was made that the 4 f orbitals contract because there are no other f orbitals below them, so they have room to contract. And so why is it that the 4 f orbitals, so that when you start filling in your electrons for cerium, here I've got 5d, and here I've got 4f, with however many boxes they have. This one's got a lot more. Why is it that when I fill the electrons in, why is it that if you look for cerium and you go in I don't know, web elements, wherever you like to look, that it turns out to be this state with 1 in D's and 1 in the F, as opposed to happily following Ohm's rule and putting 2 in there. So this was our guess. Somebody can correct us if they know better. If I put these on the vertical energy axis, I know that 4F at least has to be lower because the first electron goes there, and that one contracts. Remember, the potential due to the core sort of decays, and the 4Fs, which normally would be out here, they can contract and they can profit from the core attraction. So the first one I put there. So now I have to put another electron in. And if I were just doing single electron picture, I would put one in there and I'd be happy. Or I might even put one in here. Or I can put one somewhere in here.
But that's not single electron picture, that's due to interaction.
That's coming next.
No. Oh, you say either or.
Yeah,
Okay.
It didn't matter.
Okay.
If I follow Hunt's rule, oops, then I would put them in there. And that's only one type of interaction. So, as it turns out, it goes there. So our guess was that if you put two of them in here, in some form, say this form, because they're still on the same site, this costs you a whole bunch of energy, U. Actually, it's U prime, which may be U minus 2J. And our guess was that this separation in energy, called delta E, that this is smaller than U, i.e. it would cost you more energy to put an electron in there because U is larger than putting one in there. I tried looking up what the energy levels were, and it's basically nigh impossible. So that was our guess, at least for this one. Any comments? No? Sort of reasonable?
Good
Good guess.
That would be the
We never
on-screen.
said that you have written out the mathematicians better, so.
Perfect. I'll
That-
take it.
That has nothing to do with the U prime that we've been discussing in terms of the model of the lattice model. This is for an atom, right, we're talking about. So this would be
Right.
screens,
This would be on screen.
interorbital.
Yeah, for a Syrian atom, this would be on screen, yes.
Okay.
And the U's are very, very, very large for on screen atoms.
No.
I think it's important just to note that I think, at least I saw that somewhere, that the D and the F orbitals are usually very close together. And so you get the F's a little bit below, but it's really not enough to then be able to just fill the F completely and then leave the D out. And so you start having this partly filled orbitals.
So are you mean UFF minus UFD?
Yes. Yeah. This in this case, yeah, would be UFF minus UFD. So it costs less to have this U than having to U minus 2J in this case. Okay. So that was one. Nope, that's not what I wanted. So and there's this one, which has somewhat related. Jeroen, you got a lot of questions. Could you throw me yours? Sure. Thank you. Okay, so this question is about how do you consider orbitals in localized systems and non-localized systems. And sort of the relevant thing to look at is you need to compare T, which is an estimate of how big is your bandwidth, how strong is your hopping, your kinetic energy, how much do your electrons like to move, compared to U, which is how hard is it for them to move because there's other electrons around. Okay, so in the simplest form we can sort of look in two regimes. I can look where T over U, let's see, is much greater than 1. Okay, so that means my electrons really like to move. And this is where what Jeroen was talking about earlier, where you have your orbital energy levels. If I just sort of stick with Mark's story and separate them into TCGs and EGs, and they hybridize, and what you end up getting is you end up getting some band structure. Okay, so at this point it's not so clear that you can talk about individual orbitals, because what you really have is you have lots of electrons. On the other side, you have T over U much less than 1. Okay, now here the electrons do not like to move. So this hybridization that happened between these orbitals isn't quite as strong. It's not compared to the other skills in the problem. And so here, what you really have is you really stick with these, and they basically stay there. So the question, I think, was sort of in backwards way. It sort of went, how do you go from from atomic levels to bands back to these? But if you have a large U interaction and your kinetic energy is small compared to that, you wouldn't have made this step to begin with. You would have started from here, and this is where you would have considered the physics, because that's what the states are. So I sort of turned the question around and said, maybe we should look at it this way.
I think maybe the question maybe was also a little bit about the, there was this one picture where the T2Gs and the EGs split up, and you have two bands. And then I think in the projected subspace of the EGs, you have much higher, the effective interaction is higher. And that gives you again, that splits you again in a Hubbard way to the upper and lower Hubbard band.
Yes, but then you would simply start, okay, then I would go, well, these guys mix, these guys form a band, whereas these two.
Exactly.
Which was the other answer that was posted about the nuclides and the coexistence, where it said, well, maybe in these guys the energy, sorry. Maybe in these guys there's much more correlation, so maybe we can get magnetism from here, and these can still get.
Maybe just to comment to what he did now. The only thing that we know out of symmetry is that EG and T2G split. You have to look at the system, where you have to know why is actually the energetics different to get what is higher and what is lower. And it turns out if you have the nuclide system, it's this way, because it's slightly different symmetry, but still the same names. And if you have this kind of structure, it's this way. So just taking EG and T2G doesn't mean that necessarily one is higher than the other.
Any questions on this? Okay.
I have one very unrelated question regarding this. So, it's basically for everyone. In this limit where t is much greater than u, there, well, if you get to the limit where, if you get to the limit where u is 0, the Hilbert space is basically they are the eigenstates of momentum. Momentum is a good eigennumber. But in this case, the eigenstates are the site occupation states, like one electron per site. And I wondered if these two can be connected in any way as we change the ratio T over U, this transformation of the state space. It's something that I tried to look, but it was lost, so just put it forward. I don't know if the question is clear.
I think if we knew how to do that properly, we would be out of a job. No, I think it's a very difficult thing to do.
Okay.
And I think people use many approximations coming from either direction to try to come from this side. So here you normally come from the strong coupling limits, and here you come from the weak coupling limits. But sometimes they overlap and they work well together, and sometimes they don't. Any questions? No? You're smiling, I'm sort of terrified. Okay.
No, I love it. This is great.
All right, I got one. Because you just get to sit there.
And it's all on camera.
I have more pictures of you, so. All right, so we have one more, and I'm kind of cheating because I asked this question earlier, so I know the answer. So this was Dr. Borchardt talked about the phase diagram of, the Anderson impurity model, the DMFT, where here you have the interaction strength of some sort, maybe it's BPD, I think. Did I do that right? I think it's BPD. And you had this line, the end in critical points, where here you have an insulator, and here you have metal. And so, if you drew for us on the board what the spectral function looked like over here, And here it's sort of what you normally would expect if you go out a little bit closer to this thing. You end up with somewhat of a depression with a resonance in the middle. And then as you went over to this side, a gap opens up and the resonance entirely disappears. And the point was that sort of in between here, just going to keep going, you get something that nearly that, and you get a peak that at zero temperature necessarily has to have the same height. So I think the question asks what happens when you go around this path. So let me start from here. What I guess you would expect going up in temperature. This is around here, you get a spectral function that looks like this, but smeared by temperature, so a little more like so. As you get across this line on this side, maybe this is over here, you'd see it with a little dip, until you eventually got back over here. So you have eventually a transition from here to here, but without any first order or second order phenomena. It's just kind of smeared out back. Is that approximately right?
Horizontal axis should be U, that's for the Hubbard point, but everything else was fine.
Ah, okay. So that was pretty instant. Okay. All right. Any questions?
Well, let me just make sure I understand. The actual question that was asked in the lecture, I thought was the t equals 0 question. So then...
In the lecture, the t equals 0 question was addressed, yes.
And then the issue was the weight in the resonance just went to 0,
Yes.
right? So, okay.
Yeah.
Right.
Where it
So
gets narrower and narrower and narrower.
This is a sub-question or a
This is
related
different.
question.
Yeah. In
okay.
the lecture, we went this way.
Right.
So now, since this is a critical point, you don't have a transition anymore. Now the question was, what happens when you go around it? Because you still have to go from one to the other somehow. Okay.
Okay, I think these guys have done a great job and set a very high standard for the next group of women. So let's give them a very good